The question is, a block of mass m is attached to the lower end of a vertical spring hung from a ceiling and has a force constant k. The mass is released from rest with the spring initially unstretched. Find the maximum extension produced in the spring. This is a typical question, as if this mass which is released slowly or gradually, then the answer to this question will be different. If it is released slowly, the answer will be mg by k, and if it is released suddenly, or the question says simply it's released, then the answer will be 2mg by k. Let's analyze the two situations separately. When the mass is slowly or gradually released, this mass comes down, and every time its velocity is 0. Now, why this block remains at rest as it comes down? If we'll release it, the force of gravity is mg, and the spring force at that point, F equals to kx, is 0. So there is a net downward force acting on it. So this mass will gain velocity. That means for this motion to be done slowly, or for the mass to be at rest at every point, an external force has to be applied. If we'll draw the free body diagram of the block at an instant, then gravity is acting downwards, external force is acting upwards, spring force kx is acting upwards. As the block is in equilibrium, so F plus kx is equal to mg. As the block comes down, this x, that's the extension in the spring, goes on increasing. So this quantity goes on increasing. That means this quantity has to go on decreasing. This F goes on decreasing and finally becomes 0 at this point. And at this point, mg is acting downwards and kx is acting upwards. This is in equilibrium, and this x can't be more because we are talking about the maximum extension. So this will be the x max. So kx max is equal to mg, or x max is mg by k. Now let's discuss the situation where the block is suddenly released. At any point, if you are drawing the free body diagram, then mg is acting downwards and kx is acting upwards. Initially this kx was 0, but as the spring is gaining extension, the kx will go on increasing. So at any point of time, mg minus kx is equal to ma. The block is accelerated downwards. Its velocity is also downwards. At some point, this mg and kx will be equal, and after that the value of kx will be more than the value of mg. So after this point, the net force is kx minus mg is ma. This acceleration is upwards. The block starts from rest, and as it comes down, it's getting acceleration in the downward direction. Its velocity goes on increasing following u plus at, u being 0. At this point, it's having some velocity, let's say v, and after that this velocity goes on decreasing because of this acceleration which is in the opposite direction, and finally the velocity becomes 0. At this point, this block is getting a force mg downwards and kx upwards. This kx is greater than mg, or kx minus mg is ma. From this point, the block will move up. Acceleration is up to this point, and then from here to here, the acceleration will be downwards and velocity will be upwards following this. This means the block executes simple harmonic motion. Starts from here, goes down, gains velocity v. From here to here, the acceleration and velocity are in the same direction, so this part of the motion is an accelerated motion. Here, velocity is in the downward direction, acceleration is in the upward direction. When velocity and acceleration are having opposite directions, this motion is called decelerated motion. Again, from here to here it's an accelerated motion, from here to here it's a decelerated motion. So this is the maximum extension in the spring, X max. That means the spring would have been like this up to this, and this length is X max. Like we equalized kx max equals to mg here, we can't equalize here because kx is greater than mg. So kx max is equal to mg, we can't use. So this happens to be a different case, that between this point to this point, kx is less than mg. Here it is equal to mg, and here it is greater than mg. Let's say at some point I'm drawing the free body diagram, so mg minus kx is ma. Mg is constant. This one is not constant. This x goes on changing. Thereby, the acceleration goes on changing. And when the acceleration goes on changing, the tool available to us is work energy theorem. We have two forces acting on this block. One is the spring force and the other one is gravity, both being conservative forces. So we can conserve the mechanical energy between the points A and B. At the point A, the spring potential energy is 0 and gravitational potential energy is mg into x. This x max I'm taking as x. That's equal to, at this point, the spring potential energy is half kx squared plus gravitational potential energy is 0. So mg x is half of kx squared. From here we are getting x equals to 2mg by k. Let's see if we can use the energy concept in the first case, that is when it was released slowly, to solve the problem. The thing is, we can very well use work energy theorem, but the worry is, here we have kx, mg and an external force F. We are not given any information about this F. So this question can't be solved using work energy theorem because of insufficient data. Because if we use work energy theorem, then work done by the spring plus work done by gravity plus work done by the external force is k2 minus k1. The final kinetic energy is 0 as the velocity was 0. Initial also it was 0. This one we can calculate. This one we can calculate, but this work done by the external force F we can't calculate as it's not given to us. But had the question been Find the work done when the spring reaches the maximum extension in this case. Then work done by the external force we can calculate using this as E2 minus E1, that is K2 plus U2 minus K1 plus U1. E2 and E1 are the mechanical energies, and work done, if it is asked, by default we take work done by the external force. Let's summarize both the cases. In this case, as the block moves down at any instant, its F plus Kx equals to mg. This force goes on decreasing and is finally becoming 0, making it Kx equals to mg here. If we draw the free body diagram of the block at an instant, we have F plus Kx equals to mg. Actually, this quantity is not exactly equal to mg, it's little bit less than mg, making the acceleration approximately being equal to 0. We say at any point up to this, the body is in near equilibrium, or we say the body is in quasi-static equilibrium. When the block reaches here, its velocity becomes 0, the F vanishes, and we say the body is in total equilibrium. So, in the beginning, when the velocity was 0, there was a small acceleration down, which was making the velocity increase little bit, but we take it being equal to 0. As the block reaches here, this becomes exactly equal to mg. F plus kx, F is 0, and thereby at this position the block remains in total equilibrium. As there is no acceleration here, the velocity is 0, this block has no tendency to go down. Thereby, this distance becomes the maximum elongation in the spring. Whereas, in this case, as the block moves down, at this point, the block is in total equilibrium and nowhere else it is in equilibrium. Here, Kx is less than mg between this point to this point. Here it is more than mg. As it is more than mg here, where the velocity is 0, its acceleration is upward as the net force is in the upward direction. The block will start moving upwards, that is, it can't go below this point. Thereby, this becomes the maximum elongation in the spring. Let's see where we can use work energy theorem. As such, in mechanics, in any case, we can use work energy theorem, but preferably we use it when the acceleration is not constant, as is happening here. The acceleration is not constant here, not constant here. Here the acceleration is 0. Throughout the motion, the acceleration is not constant, it's variable. In this case, here the acceleration is approximately 0. Same case happens, here it is equal to 0. We can still use work energy theorem here, where the acceleration is constant or is equal to 0. But the only thing is, we are not using it because of insufficient information about the external force. So, when the block is released slowly, the answer is mg by k, and when it is released suddenly, the answer is 2mg by k. This case can be solved using balancing of forces, whereas this case can't be solved using balancing of forces. This case can't be solved using energy concepts, whereas this case can be solved using energy concepts.